Picture this: a vessel the size of 3 football fields, weighing 300,000 tons, cutting through ocean waves powered not by roaring diesel engines, but by the same force that carried ancient explorers across uncharted seas: the wind. It sounds like science fiction, or perhaps a romantic return to a bygone era. But this is happening right now, and it's reshaping how we think about the future of global shipping. We live in an age defined by technological acceleration. The machines that move our world have grown increasingly complex, increasingly powerful, and increasingly dependent on fossil fuels. Yet sometimes, innovation means looking backward to move forward. And that's exactly what China has done with a project that's turning heads across the maritime industry. A supertanker that marries cutting-edge engineering with humanity's oldest form of propulsion. Let's start with some perspective. Human beings have been sailing for thousands of years. Our ancestors constructed vessels propelled by nothing more than wind-filling cloth sails and human muscle-working oars. These ships carried civilizations across oceans, established trade routes, and connected continents. For millennia, wind was the undisputed king of maritime travel. Then came the Industrial Revolution. Steam engines arrived, followed by diesel power, and eventually the massive fuel-burning behemoths that dominate today's shipping lanes. These modern cargo vessels and tankers represent incredible feats of engineering. Automated systems, GPS navigation, and engines so powerful they can push hundreds of thousands of tons across the Pacific Ocean for weeks at a time with minimal human oversight. Press a button, and the ship essentially runs itself. But this convenience came at a cost, and that cost is now becoming impossible to ignore. Right now, at this very moment, approximately 50,000 commercial vessels are traversing the world's oceans. That's 50,000 ships burning through millions of tons of fuel every single day. These floating giants are the invisible backbone of global commerce, carrying everything from crude oil to electronics, from grain to automobiles. Without them, modern life as we know it would grind to a halt. Yet their environmental impact is staggering. Each ship burns heavy fuel oil, releasing massive quantities of sulfur dioxide, nitrogen oxides, and carbon dioxide into the atmosphere. These pollutants don't just disappear into the vastness of the sky. They settle into coastal communities, degrade air quality, and contribute directly to respiratory illnesses in port cities around the world. The marine ecosystems themselves suffer too, as these emissions acidify ocean waters and disrupt delicate ecological balances. The numbers tell a sobering story. According to the International Maritime Organization, global shipping currently accounts for roughly 3% of all carbon dioxide emissions worldwide. That might not sound catastrophic until you realize what 3% actually means in absolute terms: nearly 1 billion tons of CO2 annually. And here's the alarming part. If current trends continue unchanged, that proportion is projected to balloon to 17% by the year 2050. Think about that for a moment. We're talking about a nearly 6-fold increase in just 3 decades. While other sectors are scrambling to decarbonize, the shipping industry has lagged dangerously behind. This isn't happening in a vacuum. More than 130 countries and regions worldwide have now committed to achieving carbon neutrality, essentially pledging to eliminate their net contribution to atmospheric carbon dioxide. These aren't just lofty promises. They represent fundamental shifts in how nations approach energy, transportation, and industrial production. On land, we've seen remarkable progress. The renewable energy sector has exploded over the past decade. Between 2010 and 2020, global capacity for wind and solar power surged from approximately 120 million kilowatts to over 700 million kilowatts. That's nearly a 5-fold expansion in just 10 years. Electric vehicles have moved from niche curiosity to mainstream transportation option in many markets. Cities are investing in public transit, bike infrastructure, and pedestrian-friendly design. But the oceans? That's where things get complicated. Ships can't simply plug into charging stations. The distances are too vast, the energy requirements too immense, the infrastructure too costly. Liquefied natural gas has emerged as a cleaner alternative to traditional marine fuel, reducing certain emissions significantly. Yet adoption rates remain frustratingly low across the global fleet. The economics, the port infrastructure, the retrofitting costs, all of these factors create barriers to rapid change. And then there's the catastrophic risk of oil spills. When maritime transport goes wrong, the consequences can be apocalyptic for marine environments. Oil tankers carrying hundreds of thousands of tons of crude represent floating environmental disasters waiting to happen. When these vessels rupture or sink, thick layers of petroleum spread across the ocean surface, blocking sunlight, preventing oxygen exchange, and killing marine life wholesale. The Prestige disaster in 2002 remains seared into environmental memory. When that tanker broke apart off the coast of Spain, it released 77,000 tons of heavy fuel oil into the Atlantic. The resulting contamination devastated hundreds of miles of coastline, destroyed fishing communities, killed countless birds and marine animals, and took years and billions of dollars to partially remediate. The scars remain visible today. Recognizing the urgency of this crisis, the International Maritime Organization established ambitious new requirements in 2022. The mandate is clear. The global shipping industry must reduce carbon dioxide emissions to half of 2008 levels by 2050. This isn't a suggestion or a guideline. It's a regulatory requirement backed by international agreement. For ship owners and operators worldwide, this creates an existential challenge. How do you cut emissions in half while simultaneously meeting the growing demand for global trade? How do you retrofit or replace a fleet of vessels that were designed for a fossil fuel world? Where do you find the technology, the investment capital, and the infrastructure to make this transition? Different nations have approached this problem from different angles. Some are betting on liquefied natural gas despite its limitations. Others are exploring hydrogen fuel cells, ammonia propulsion, or battery electric systems for shorter routes. Each approach has advantages and drawbacks, costs and benefits. And then there's China's solution, one that almost nobody saw coming. China has become synonymous with electric vehicle adoption. The transformation has been nothing short of remarkable. In 2018, roughly 1 million electric vehicles were on Chinese roads. Today, that number exceeds 5 million and continues climbing rapidly. This isn't just about consumer choice. It represents coordinated industrial policy, massive infrastructure investment, and a fundamental reimagining of personal transportation. The environmental benefits have been measurable and significant. Over the past 5 years, the proliferation of electric vehicles has helped China reduce total air pollutant emissions by approximately 1/3 in many urban areas. That's cleaner air for hundreds of millions of people, fewer respiratory illnesses, and a meaningful dent in the country's overall carbon footprint. But China didn't stop at land transportation. With the world's largest shipbuilding industry and one of the most extensive merchant fleets on the planet, Chinese engineers and policymakers recognized that maritime transport represented both a massive challenge and a tremendous opportunity. Here's where the story takes an unexpected turn. Rather than simply copying Western approaches to cleaner shipping, Chinese researchers decided to resurrect a technology that had been abandoned for more than a century. They looked at sails, not the canvas rectangles of old sailing ships, but modern, high-tech wind capture systems designed with aerospace precision. In 2015, China launched what it called the Sail Technology Demonstration Application Development Program. The name might sound bureaucratic, but the ambition was revolutionary. Could modern engineering resurrect wind power as a viable supplement or even alternative to fossil fuel propulsion for massive commercial vessels? This wasn't a hobby project or a publicity stunt. It was a serious, well-funded research initiative that brought together naval architects, aerospace engineers, material scientists, and maritime industry experts. The goal was to develop airfoil sail technology that could actually work on the scale required for contemporary shipping. 3 years of intensive research and development followed. Engineers faced countless challenges. How do you design a sail strong enough to withstand hurricane-force winds, but light enough not to destabilize a vessel? How do you create a system that can be controlled automatically without requiring a crew of experienced sailors? How do you integrate this technology into ships designed around diesel engines and propeller systems? By 2018, they had their answer. The research team had not only mastered the fundamental principles of airfoil sail design and manufacture, but they had also achieved what international maritime experts acknowledged as world-leading capabilities in this specialized field. The real test, however, wasn't in the laboratory. It was out on the open ocean. Enter the Kylie, a 300,000-ton very large crude carrier, or VLCC in industry terminology. These vessels represent the giants of ocean transport, capable of carrying 2 million barrels of crude oil in a single voyage. They're essential to global energy infrastructure, moving petroleum from extraction points to refineries worldwide. But the Kylie is different. This supertanker became the first VLCC ever equipped with modern airfoil sail technology. The installation is genuinely spectacular. Mounted on the deck are enormous metal sails, each standing nearly 40 meters tall, about 15 meters wide at maximum extension, with a base diameter exceeding 5 meters. These aren't decorative additions. They're precision-engineered structures designed to capture wind energy and convert it into forward thrust. The visual impact is striking. Imagine standing on a dock, watching this massive vessel approach, its metallic sails towering above the deck like the fins of some giant mechanical fish. It looks simultaneously ancient and futuristic, a ship that could belong in the age of exploration or in a science fiction vision of sustainable transport. But the real question isn't aesthetics, it's performance. Does this actually work? The initial results from the Kylie have been encouraging, though perhaps not as dramatic as some might have hoped. The airfoil sail system has demonstrated the ability to reduce fuel consumption by approximately 3% under optimal conditions. 3%. To someone outside the shipping industry, that might sound modest, even disappointing. Why bother with all this engineering complexity for such a small gain? But context is everything, and in the maritime transport world, 3% is actually transformational. Consider the scale we're dealing with. A conventional 300,000-ton oil tanker cruising at 15 knots, a typical operating speed, burns between 70 and 90 tons of fuel every single day. That's not a typo. Every 24 hours, one of these vessels consumes roughly the same amount of fuel that might power a small town for a month. Now apply that 3% reduction. Suddenly, we're talking about saving between 2 and 3 tons of fuel daily. Over a typical voyage from Asia to Europe, a journey that can take several weeks, those savings accumulate into tens or even hundreds of tons of fuel that never gets burned. Fuel that doesn't need to be extracted, refined, transported, and loaded. Fuel that doesn't produce carbon dioxide, sulfur compounds, or nitrogen oxides when combusted. Multiply that across multiple voyages per year, and the numbers become genuinely significant. Let's zoom out even further. Chinese shipping companies operate tens of thousands of vessels across global trade routes. These ships collectively represent a massive carbon footprint, one that will only grow as China's economy expands and its trade relationships deepen. Researchers have calculated that if the Kylie's sail technology were implemented across the fleet, each equipped vessel could eliminate approximately 3,000 tons of carbon dioxide emissions annually. That single number deserves unpacking because it's easy to become numb to large figures without proper context. 3,000 tons of CO2 per ship, per year. That's equivalent to the total annual emissions from roughly 2,000 passenger vehicles. Put another way, achieving that same carbon reduction through tree planting would require cultivating and maintaining about 160,000 trees until maturity. Now imagine scaling this across hundreds or thousands of vessels. the cumulative environmental benefit becomes genuinely meaningful in the context of national and global climate commitments. This isn't just incremental improvement. It's a pathway toward fundamentally altering the carbon profile of one of the world's most emissions-intensive industries. Beyond climate impact, there's also the economic dimension. Fuel costs represent one of the largest operating expenses for shipping companies. Even modest improvements in fuel efficiency translate directly to bottom-line savings. In an industry where profit margins can be razor-thin, especially during downturns in global trade, any technology that reduces operational costs while simultaneously meeting environmental regulations becomes extremely attractive to ship owners and operators. Of course, no technological innovation arrives without criticism, and the Kylie's sail system has faced its share of skeptical scrutiny. Some of the most pointed questions have come from maritime researchers and industry experts in Japan and South Korea, two nations that have long dominated global shipbuilding and, maintain competitive tensions with China's rapidly expanding maritime sector. The central concern these critics raise is fundamentally practical. What happens when the wind doesn't blow? It's a legitimate question. Wind is inherently variable and unpredictable. While certain ocean routes benefit from reliable trade winds and prevailing weather patterns, approximately 10% of the world's ocean surface experiences frequent calm conditions where wind speeds drop to near zero. A ship that relies entirely or primarily on wind power could find itself, effectively stranded during these windless periods. In the age of just-in-time global supply chains, where delays can cascade into massive economic disruptions, the prospect of cargo ships sitting motionless, waiting for favorable weather, raises some serious operational concerns. There are also safety considerations. Modern vessels carry supplies calculated for expected voyage durations with appropriate margins. Extended delays could potentially strain food and water provisions for crew members, though this risk is probably overstated given the safety margins built into maritime logistics. The critics from Japan and South Korea have essentially argued that wind propulsion, while romantic and theoretically appealing, introduces too much unpredictability into a system that demands reliability and precise scheduling. But here's what's crucial to understand. These criticisms, while worth taking seriously, are based on a fundamental misunderstanding of how the Kylie and similar vessels actually operate. This is not a sailing ship in the traditional sense. The Kylie is not abandoning diesel engines in favor of becoming a pure wind-powered vessel. Instead, the airfoil sail system functions as a hybrid supplement to conventional propulsion. The ship retains its full diesel engine capabilities. The sails don't replace the engines, they augment them. When wind conditions are favorable, the sails contribute thrust, reducing the load on the engines and therefore decreasing fuel consumption. When wind is insufficient or absent, the ship continues operating exactly as a conventional tanker would. This hybrid approach is actually brilliant because it eliminates the primary vulnerability that critics identify. There's no scenario where the Kylie gets stranded in calm seas. At worst, during windless conditions, the vessel simply operates like any other tanker, with perhaps a marginal weight penalty from carrying the sail equipment. At best, in ideal wind conditions, fuel consumption drops significantly, delivering all the economic and environmental benefits that make the technology attractive. Moreover, Chinese engineers haven't been sitting idle in the face of these criticisms. Active research continues on optimizing sail design to improve wind capturing efficiency even in lighter wind conditions. Advanced materials, refined aerodynamic profiles, and computer-controlled adjustment systems are all areas of ongoing development. There's another dimension that critics sometimes overlook. Modern maritime navigation is extraordinarily sophisticated. Ships don't simply point in a direction and hope for the best. They use weather routing systems that integrate satellite data, atmospheric modeling, and historical weather patterns to optimize routes in real time. These systems can predict wind conditions days or even weeks in advance with reasonable accuracy. Ship captains and navigation officers can plan routes that maximize exposure to favorable winds while avoiding calms. They can adjust course dynamically as weather systems evolve. This level of meteorological intelligence was completely unavailable to sailors even 50 years ago. By combining modern weather routing with hybrid propulsion systems, ships like the Kylie can strategically capitalize on wind energy when available, while maintaining schedule reliability through engine backup. It's not an either-or proposition. It's an optimization problem, and one that modern computing systems are exceptionally good at solving. The current 3% fuel reduction achieved by the Kylie represents first-generation technology, a proof of concept that demonstrates viability. But researchers are confident that continued refinement can push efficiency gains substantially higher. Industry experts suggest that advanced sail systems, optimized routing algorithms, and improved integration between wind and engine propulsion could realistically achieve fuel consumption reductions of 20% or more. That would represent a transformational change in maritime economics and environmental impact. 20% less fuel means 20% fewer emissions. It means proportionally less demand for petroleum extraction and refining. It means reduced operating costs that could make shipping more economically sustainable, even as environmental regulations tighten. And it means a technology pathway that could help the global shipping industry actually meet those ambitious 2050 carbon reduction targets that currently seem almost impossibly distant. For countries struggling to reconcile economic growth with climate commitments, technologies like China's wind-powered ships offer a rare win-win scenario. They reduce environmental harm while potentially lowering costs. They advance technical capabilities while addressing regulatory pressures. They demonstrate innovation while building on ancient, proven principles. This development doesn't exist in isolation from broader competitive dynamics in global maritime industries. For decades, Japan and South Korea dominated international shipbuilding. Their yards produced the majority of the world's commercial vessels, and their engineering expertise set global standards. But over the past 5 years, that landscape has shifted dramatically. Chinese shipyards have expanded production capacity, improved quality standards, and aggressively pursued market share. China's ship exports have grown consistently year after year, and the country has now surpassed both Japan and South Korea to become the world's leading shipbuilding nation by most metrics. This ascendancy hasn't been purely about volume or price competition. China has also invested heavily in maritime technology research and development, seeking to establish leadership not just in building conventional ships, but in defining what the next generation of vessels will look like. The Sail Technology Program fits squarely into this strategic vision. If China can establish technical leadership in hybrid wind propulsion systems, it positions Chinese shipyards to capture a growing market as environmental regulations force fleet modernization worldwide. The intellectual property, the manufacturing expertise, the operational experience, all of these create competitive advantages that could translate into commercial success and significant foreign exchange earnings. Here's where the story takes an interesting turn. The questions and criticisms raised by Japanese and South Korean researchers, while perhaps motivated partly by competitive concerns, actually represent valuable input that Chinese engineers can use to refine and improve the technology. Rather than dismissing these critiques or responding defensively, accepting them as legitimate technical challenges creates opportunities for advancement. What if Chinese researchers specifically address the calm wind scenarios by developing more efficient, low-wind sail configurations? What if they create superior weather routing systems specifically optimized for hybrid propulsion? What if they establish the operational protocols and training standards that make these vessels more reliable than critics predict? Each challenge overcome becomes a demonstration of capability. Each problem solved becomes proprietary knowledge. Each improvement becomes a selling point for future customers considering whether to invest in this technology. In a paradoxical way, skepticism from international competitors might actually accelerate Chinese innovation in this space. The pressure to prove critics wrong, to demonstrate that the technology works under real-world conditions, to establish commercial viability, all of this creates powerful incentives for continued investment and refinement. Step back from the technical details and competitive dynamics for a moment and consider what this development represents at a more fundamental level. We're witnessing a genuine reimagining of how large-scale transportation might work in a carbon-constrained future.